People, let's start to talk about finding centers of mass for non-trivial objects. The ones that I've drawn on the bottom here, I would characterize as trivial. Why are they trivial? Because they contain one, if not two, if not three degrees of symmetry. Right? Symmetry means that there's an axis around which something could be rotated or flipped, and you might not even be able to tell. All right, so if this has a, if not for putting a red dot on the end of this one, if I were to rotate this thing 180 degrees around that axis, if not for the red dot being there, you'd never know. Similarly, if I were to rotate this form around this axis, if not for that side colored red, if I rotated 180 degrees, you wouldn't know. If I were to rotate this form about that axis, if not for this side being painted blue, you'd never know. And so on and so on. So these are, quote, trivial objects, the ones in the bottom. Locating their centers of masses, there's no special techniques needed. We just know that the centers are in the center of that dimension. But we're going to use some ideas that we develop from here to find centers of masses of non-simple form. Okay, so we're going to start with our definition of where the position of center of mass is. Well, that has to do with the product of all individual discrete masses and their locations divided by the sum of all masses. All right, so we can turn this into something else. Because if we say that a system isn't this object and that object and this object, but a whole bunch of objects that, well, like for example, in a continuous body like this, an extended body, some would say, what we can do is say, well, let's consider the fact that an object is made of lots of little parts. And we can say that the center of mass we can actually take as a limit when an object is made up of a ton of objects that are really, really small. All right, so we look at the limit of how small do these masses get, and then, well, each one of them is still located at a certain place. And there's still some total. But if we're saying that each mass gets smaller and smaller and smaller, what we really end up doing is saying that this is the same as saying that center mass can be taken as the integral of x dm over big M. All right, and what that means is that the center of mass is, well, really adding up all of the, that's what the integral really means. Now this is the product of, this x still means location of center of this dm. Well, what's that dm? That dm is a tiny, really tiny, infinitely tiny, tiny element of mass. And then the big M here is just still the system's whole, the object's entire mass. And again, location along the x-axis relative to a certain defined origin, sure. All right, and we can do the same thing for a y center of mass if needed, or a z center of mass. Now, let's get down here and talk about what we're going to typically do when we have forms that occupy space in well, varying numbers of dimensions. And we're going to do that by sort of by standardizing standardizing mass. All right, standardizing mass. All right, because we got to talk about what are the little parts. Right? What are the little parts? That's part of your process when we find centers of mass will be, identifying what is my dm, what is my tiny little element of mass, and what does that object's mass depend on. All right, and so to do that, we can define sort of three different ways in which mass can be related to stuff. So if this is a rod of mass m and length L, we can typically say that this thing has a length, or a, excuse me, a linear density. In many examples, linear density will be constant. All right, so linear density by definition is mass per unit length. And therefore, we can say that the mass of some object is lambda times L. And then from there, we can probably say, well, if the whole thing has a mass m, that's lambda L, then a little part of it come here. Then a little part of it.
Please excuse the interruption. We're going to continue in a line.
So that means that, if we're saying that, hey, here, this little thing right there is my dm. Well, that little dm, the mass of that little element, depends on how dense this thing is, and, well, this tiny little immeasurably small dm. Right? Whole mass turns to dm, whole length turns to dm. Yeah? Okay. Now, here is a two-dimensional object of, I don't know, area A. And here, we define sigma as an area density, where sigma is mass per unit area. And therefore, mass can be written as sigma A. And then what you might do is say something like, well, this thing here is my dA. And then we can say, well, my dm is sigma times dA. Now notice, I called this my dm. Sure, this is also my dm, but the mass of that thing depends on its area. Its area is dA. And the mass depends on its density, which we're assuming is uniform. Now, we could probably also define what this area is, what our dA is. Well, our dA has that height and has this little tiny width. Little tiny, right? We're talking about little tiny things. Here's a box that has a volumetric density, or rho is mass per unit volume. And so there's a slice, well, sorry, we can write the mass of this thing as rho times volume. And there's like a slice of this block that is, call it what you want, call it your dm. Sure, that slice has a mass, and that dm is rho dv. Now this dv, well, that element of volume has that height, say, and that depth, and again, this little tiny thickness. So we could expand this dv to say, what are the parts of that? All right, but we got to get comfortable with when is it appropriate to use each of these expressions for density based on the form that we're using. Are we talking about a linear object or a one-dimensional object or a two-dimensional object or a three-dimensional object? All right, so let's talk through a couple of examples. Now, this one is trivial for sure. We know where the center of mass of this rod of length L is. I mean, of course, it's right here, right? It's in the center. We better. The reason we do this is to point out that we can apply our new expression for center of mass to a trivial example, and we better get what we expect to get. Okay, so if we say that relative to this place right here, the position of the center of mass is by definition x dm over m. Now, this is a number. It's a constant. I'm going to pull it out front and turn it into this. Yeah. Now, let's say, assume uniform linear mass density. All right, so here's what we got to do. Right, the position of the center of mass of each object, like here's one, here's an elemental object. Here's our little dm. Well, let's see, dm. The deal is, what we want to do is we want to get this integral to be a variable, d that variable. Because x is a variable. X varies. X could be this far, or this far, or this far, or this far. Right? So x is a variable, but we're trying to integrate dm. So you can't do that. All right? What we need to get is to a place where we have a variable and integrating with respect to that variable. All right? So since x varies, we can't integrate that variable with respect to some different variable. That means we got to write dm in terms of dx. So here's that. Remember, we say something like, let's define, we can start here. Well, our linear mass density is mass per unit length. That means that our mass is lambda L. That means that each individual dm can be written as lambda dl. Well, notice, here's a dl. A little tiny length. Well, and here is x for that dl, and notice that dl is in the direction of x, so we can call it dx. All right, so I'm going to write this as lambda dx. And then I'm going to take our expression, x, position of the center of mass is 1 over m times x. Now, dm, lambda dx. Nice thing about this is now, let's see, now lambda's a constant. I'm going to pull that out. Constants don't get integrated. Only variables get integrated, so we do x dx. Now, what does x vary from? Remember, x is a variable. The first position of the first object that's right here is located, well, at position 0 relative to the origin. The last one out here is located at position L relative to the origin. Those are our limits of integration. This is an easy integral. I hope so. It's a simple form. So we have lambda over m times x squared over 2, evaluating from 0 to L. Right? Here's this. Integrating x dx gives us x squared over 2. So we evaluate, that means, quite literally, I mean, you might not write this, but it means, okay, we have to do L squared over 2 minus 0 squared over 2. Some of my dudes are a little quick or perhaps improper when evaluating integrals using their limits. Okay, sure, that goes away. So what do we get? All right, we get that the position of our center of mass is lambda over m L squared over 2. But what's lambda? Oh yeah, lambda is m over L. So we get m over L over n times L squared over 2. Or we get, well, M over L over M is that, times L squared over 2. And let's see, M, 1, L with a factor of L. There's a 1. Okay, guess what we get? L over 2. Miracle? No, just calculus. Okay? So, this idea of identifying what the thing is that you're talking about and how can we characterize it, particularly with respect to the variables we want to use to integrate, now that's the trick to these. Let's look at another one. Here's a two-dimensional, looks pretty simple-ish, but here's a two-dimensional triangle. Length and width, all right, fine. How about we call this like a height instead? A length and a height. And here's a position from which to define the position of the center of mass in the x direction at least. Well, I'm going to do this. Okay with that? All right, so what's my dm? Now, let's assume this thing has a uniform area density sigma. That means that sigma is mass per unit area, or mass is sigma times A, or dm is sigma dA. So we want to find a dA, a little area, specifically one that we can identify the position of the center of mass of in the x direction. And so what that means is, if we take something like this, well, this thing has a center of mass, the center of mass of this infinitely small strip is on that line. So here's my x. That thing is my dA and or my dm. All right, so here's my dm. And my dm is sigma dA. So what's the little tiny area of that little object? Because again, what we can't do, at least we could write this if we want as x, well, right, x is a variable because x could be this, or this, or this, because there's little things here, and here, and here. So we can't integrate a variable with respect to a different variable. And even if I say, well, dm is phi sigma times dA, I still can't integrate variable b, or d, a different variable. So can I express dA in terms of dx? Well, I can't, right? This thing has, let's call this a height lowercase h. And a width, well, guess what? dx. Right? I'm taking this little strip that, right, there's this thing here. So is the quote height really h? Well, if it's skinny enough, it is. And it is skinny enough because it's infinitely skinny. dx is infinitely skinny. So we can write this as 1 over m x sigma dA. Well, our dA is h dx. But h is a variable, right? H could be tiny. H could be big. So what's the height of any one of these things? Well, it depends. It depends on how far out along the x-axis you are. And let me clean up a little bit here. We can identify a couple of similar triangles. Here's one. The one that has the thing we want, and it looks like this. And then there's the whole triangle. And so the similar triangle thing says that our x and that h is similar to this whole L and the whole big H. So we can say that h is to little x as big H is to the whole length of this thing. And look at this. We can now say that h is x times h over L. And now we can get rid of h and write it in terms of x. All is good in the world. So, x, sigma, h is x, h over L, dx. What does x vary from? Because now we're down to, let's see, constant, 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 variable, variable, d that variable. Good. So what does our variable vary from? It varies from 0 out to big L. Now again, these constants, I'm going to yank them out the front. All right. So we got sigma h over L. We do have this m, and then we integrate from 0 to L, x squared dx. So that's sigma h over ml. Well, if you integrate x squared dx, you get x cubed over 3. We evaluate from 0 to L, which is sigma h ml, whoops, here I'll let you get away with it. It's just L cubed over 3. Yes, minus 0 cubed over 3. But I'll leave it at that. Here's a factor of L that I'll take out. And so we get the position along the x-axis of the center of mass of this form is sigma h L over 3n. That's kind of ugly, but let's unpack this a little bit. Well, sigma over n. All right, well, let's see. Sigma is mass per unit area, that's this part, times HL over 3m. So we can ditch the mass. HL over A, well, let's see, HL, now A is 1/2 base times height. There's this 3. No. Except, sorry, I dropped this squared. So look, now we get a L goes with an L, and H goes with an H, and we get L over 3/2. Well, that's the same as 2L over 3. How about that? The center of mass of this triangle is 2/3 the way along the edge from the point. Yeah? So what's that mean? Well, now it ain't really symmetry, but it's maybe conceptual symmetry. It means, let me reproduce, hang on 1 second. This means that there is a center of mass 2/3 of the way along from the point along the x-axis. So from the point to the right angle, 2/3 of the way along. Well, guess what? There's, in the y direction, if we take 2/3, there's a point from the point to the right angle, 2/3 of the way along there, where the center of mass is. And there's the center of mass. So, not, like I said, not exactly symmetry, but maybe conceptual symmetry. If we've defined that along this direction from the point to the right angle, the center of mass is 2/3 along the way. Perhaps it follows that if you went from here down, from, again, the point to the right angle, 2/3, because what would change? Well, you could derive, if you did the y part of it, you'd have things, DMs that look like that, or you're still doing similar triangle stuff, right? Where you'd have this triangle and the whole triangle, end up with 2/3 of the way down. All right, so XCF for a triangle is 2 L over 3, and YCM, again, measured from up here is, well, what do you want to call it, negative 2H over 3. This is L, and this is H. And it doesn't matter the shape of the triangle. It doesn't matter if it's a super skinny like this. It doesn't matter if it's, you know, like that. Any kind of right triangle. Is that true, right triangle? Certainly right triangle. Any triangle? Yeah, it's got to be any. It's got to be right triangle, right? We couldn't do this. Yeah, right, and right. Yeah, any right triangle. You now know where the center of mass is, which is great. I mean, is it great? I don't know. It's not great, but guess what? You can use this fact in some different harder problems, and that is great. Okay. See you soon.